I guess I'm just a play date to you.
Assalamualaikum and hi. Today our group will present one of power electronic topic, which is DC to DC boost converter. Before we start, we will know what in this project. First, we will know about analyzing, second, operation, and third, simulation of DC to DC boost converter. First, analyze. Generally, DC to DC boost converter is a boost converter without isolation that is used to step up an input voltage to some higher level and required by a load. The step-up converter means output voltage is greater than input voltage. Next, a DC to DC converter, also known as DC chopper, is a static device which is used to obtain a variable DC voltage from a constant DC voltage source. Also, the DC to DC boost converter is defined in more general way as an electrical circuit that transfers energy from a DC voltage source to a load. Example is when we have only 5 volt of battery, but in this case we need 12 volt. So the question is, can we convert one DC voltage to another one? And the answer is yes. That's how DC to DC boost converter do. Convert one DC voltage to another one.
Okay, for the operation of DC to DC boost converter circuit, in this circuit we have one voltage source, one inductor, one diode, one switching device, one capacitor, and one load. In this operation, we have 3 conditions, which is the first condition is when switching device is off. Nothing gonna happen because the output capacitor is charged to the input voltage minus 1 diode drop. For the second condition, when switching device is on, all the current is moved a flow through the switching device and through the inductor. At this point, the output capacitor stays charged since it cannot discharge through the now back bias diode. You also have to note the polarity of the voltage applied across the inductor. And for the last condition, when the switching device is turned off and the current to the inductor is stopped abruptly, you have to note that the inductor now acts like a voltage source in the series with the supply voltage. This means that the anode of the diode is now at the higher voltage than the cathode and is forward biased. The output capacitor is now charged to the higher voltage than before, which means have a successfully step up low DC voltage to the higher one. Okay, for DC to DC boost converter, we have 2 equations, which is the first is output voltage equation. In this equation, voltage output is equal by voltage input divided by bracket 1 minus D. For the second equation, we have output voltage ripple equation. In this equation, output voltage ripple equal by V output multiplied by dt and divide by RC. Or we can use the voltage output multiplied by D and divide by RCF.
About simulation. From this slide, we can see the block diagram. The component in block diagram is DC voltage source, inductor, MOSFET, diode, capacitor, load, current and voltage measurement, scope and display, and plus generator. V output for block diagram is 99.21 volt. From the table, we can see the parameters and value. For resistor, we use 50 ohm, capacitor 100 microfarad, inductor 400 microfarad. Frequency, we use 25 kilohertz, duty cycle 0.5, simulation time 2 seconds, input DC voltage 50 volt. From this slide, I will explain about waveform of the T-cycle signal, also known as a ratio of MOSFET on time to period. The T-cycle is the ratio of time a load or circuit is on compared to the time the load or circuit is off. It is called the T-factor, expressed as a percentage of on time. For example, 60% the T-cycle is a signal that is on 60% of the time and of the other 40%. Here, we use 0.5 the T-cycle, that means 50 on and the other is off.
Next, waveform of output voltage. How we get the waveform is, we connect the current measurement to the load. And here, we have two waveforms. The first one is before zoom, and the second one is after zoom. After zoom waveform is also known as output voltage ripple. Next, calculation. We have two equations here, output voltage and output voltage ripple. For output voltage, V0 equals to V in divided by 1 minus D. For output voltage ripple, V0 equals to D multiplied by R, C, and F. Next, waveform of inductor current. How we get the waveform is, we connect the current measurement to the inductor. And here, we also have two waveforms, the first one and the second one. If we zoom the first waveform, we will get the second waveform, which is maximum and minimum inductor current. And in this case, the maximum is 5.3 ampere and minimum is 2.8 ampere. Next, calculation. We have calculation for maximum and minimum inductor current. For maximum inductor current, the equation is I max equals to Vs divided by 1 minus D power 2 multiplied by R plus Vs multiplied by D and T divided by 2 multiplied by L. For minimum inductor current, I min equals to Vs divided by 1 minus D power 2 multiplied by R minus Vs multiplied by D and T divided by 2 multiplied by L.
Verification through experimental result and calculation. From this slide, we will compare about simulation and calculation. First table is output voltage. From simulation, we'll get 99.21 volt and calculation will get 100 volt. The second table is maximum and minimum inductor current. For simulation, from maximum inductor current will get 5.3 ampere and calculation maximum inductor current will get 5.25 ampere. And simulation From minimum inductor current, we'll get 2.8 ampere, and calculation from minimum inductor current will get 2.75 ampere.
Okay, in conclusion, we know the experiments are well conducted, and we also able to use the MATLAB simulation smoothly and faster than before. We also know the difference between simulation and calculation are too small. Hence, if we round off the value, it will get exactly same. Thank you.